Hey folks, welcome. Just want to make sure you get this going here. Yeah, so this is going to be just a little tutorial on some of the most important parts of what I think of atomic history and the atomic theory in most likely just like a few minutes here. So let me just get this going here. I apologize. There's a lot of new tech that we're working on. So first of all, we're going to start with the ancient Greeks. Now, really like the I really like the let me get this here. I really like Adam Smith for a couple of reasons because it shows the context in which all this stuff was taking place. So if you're at Adam Smith, we're going to start here. We're going to go to atomic theory timeline, and here are the things I'm going to point out that are probably the most important. So it starts a long time ago, and what I like about this is they talk about people who did believe in the atomic theory. Those people, the anti-atomists in red. Okay, and then people who weren't quite sure in neutral. So we're going to start back, and the grandfather of all was Democritus. He pretty much started out, and he basically said that you just chop stuff up till it gets small enough, and it gets to the point where you can't cut things in half anymore, and you're going to get down to a tiny little piece, and that little piece is called an atom or a part, and that there was also a void, and that was really controversial at the time because many people, philosophers, didn't really believe in a void. But this is where the idea of atoms being really small things and starting off as first came up with. And they thought they're round because, well, every time you look up at the sky, things are round. So step number one, that's where we first get the word atom. Okay. Now, that's nice, but what happens is the atomic theory works great, but there's no experiments. So we keep going and we talk about the classical nature and all this stuff and keep going. And then all of a sudden, right away, we start getting to, let's see, get here. So we start getting to, there we go. We start getting to the Age of Enlightenment and atomic theory and all that good stuff. And the one I really want to point out here is a guy named Dalton. And Dalton basically came up with these ideas. So Dalton is right here. He was a teacher, and he basically had these, and I would write these down. Okay, this is really important. His atomic theory said, look, all matter is made up of these little pieces called atoms. They're tiny, indestructible building blocks. They're all identical, and these atoms are indivisible. And if you have different elements, you have different atoms, different sizes. And if you have the same element, you've got the same types of atoms. When compounds combine to form atoms, they form in the same whole number ratio. So water will always be 2 H's and 1 O. It'll never be like 2.5 H's and 1 O or H4O, any of those. And he also said that chemical reactions, when compounds react, you keep the same atoms, they just rearrange and recombine. The biggest thing that's really important here is that it's the concentration of mass. You can't create or destroy mass. It's conserved, it's rearranged. And so that most of what he's talking about is what we still have today. It took away some of the idea of philosopher's stone and things like that. The only thing about Dalton that we're not quite sure about, that he wasn't sure about really, which didn't know about, was this thing called isotopes. So elements have the same atoms, but they can have slightly different masses, which are called isotopes. We'll talk about that later. Okay, now let's go back to the atomic theory. So this is great, but we needed a lot of evidence, and it started out with one guy I'd like to show you real here is Thompson. And J.J. Thompson's kind of, as you can actually see his paper here. Think about turn of the century, 1900s. He had the plum pudding model. Okay, and here's what Thompson had. So the idea is that and we actually have one. This is called a cathode ray tube, and basically you've got copper and zinc. And I'm going to turn this on. Right, so we're going to turn this on, and so what happens is these electrons. Or sorry, they didn't know they were electrons. These little pieces come flying out of the cathode and they hit the zinc anode, which is positive. And then one of the things that happened was he decided to put a magnet up to it. And when he put a magnet up to it, it would bend that stream, okay? And he could block the stream and all that. And he knew that these things were real small. And if you flip the magnet, something else happened. They would go closer to it. Now, here's the most important thing you need to get down with Thomson. No matter what gas was used, you had the same tiny little particles doing the same thing. So he said these must be true for any atom. He came up with the first idea of subatomic particles, that there's something true for all atoms. And what he found there were these little pieces called electrons. And so hopefully you can see this better. I'll change the background here so it makes it a little better. So you can see these things called electrons. And of course, he didn't call it that at the time. And then he decided to come up with this idea based on this called the plum pudding model. Now, it should be said that Thompson was kind of an important guy, and the plum pudding model was like this. And so he said, look, the plum pudding model, this whole thing right here is basically a giant blob of pudding, like a positive charge. And these are these tiny little negative charges. And that's what he got the plum pudding model. So he hired a guy from New Zealand called Rutherford. Okay. And Rutherford came in and did the next model. And he was really, and Thompson basically said, look, Rutherford, I need you basically to prove my model correct. Well, funny thing happened. Okay. Here's what Rutherford did. And this is called the gold leaf experiment. Rutherford's like considered the father of sort of atomic theory. He took these alpha particles, and we're going to load the model here. And basically here it is. Okay, so we're just going to load this experiment. So here's this little positive particle shooting in. So this whole thing should be positive with little negative pieces in here according to the plum pudding model. And we're just going to fire these shots at it. Okay, we're just going to keep on firing and watch what happens. We're going to fire and fire as many as we can, hopefully. And this is, we're seeing some lag time here. But essentially what happened was Rutherford figures out that, as you can see, 99.9% of the atom is made up of empty space, which did not prove the plum pudding model at all. It had a super dense inside, which is the nucleus, which is where all the mass is. You had tons and tons of space. Then you had these electrons way on the outside, kind of like this planetary model. They didn't know much about those electrons. And basically, if you take my fist, for instance, and you blow it up to the size of a nucleus, according to the gold leaf model, the first electron would be anywhere from 5 to 10 or 2 to 3 miles away. If my nucleus were a proton, or my fist were the proton, it'd be about the size of a beach ball. The electron would be about the size of a BB. If you were to take a 14-story building, you could imagine the electron on the bottom floor or the top floor. On floor 7, you would find the nucleus about the size of a kind of a large BB. And if you were to go to pick it up, you couldn't, because it would weigh about the size of a dump truck. Thompson kept on telling Rutherford, surely you must be wrong, because that doesn't prove my model. Rutherford said, no, I think I am. So finally, they were at a conference together, and Thompson had fallen asleep in the front row. And Rutherford had this model for 2 years now and hadn't told anyone, because Thompson kept on telling him, you must be wrong. So finally, Rutherford said, look, here's this gold leaf experiment. And essentially that blew the lid off of everything. That's what we now know is the atom is made up of. It's this idea that you have this positively charged center where most of the mass is. It's pretty small. It's where most of the mass is positive charge. You have a ton of empty space. And then way on the outside, you've got these electrons going at almost the speed of light, going really, really fast. And it gives the perception of volume. And it's and Rutherford didn't know anything about the electrons. He just assumed it was kind of like planets going around the sun, which we'll find out later on. Not quite true. So that's it. And that's the basic parts.